So our topic for today is topological semimetals, especially NMR measurements, which we've done in my lab. I explain some details of how that works. But this is an overview of where we're going. So let me go ahead and get started here. So Dirac semimetals, so the topological semimetals include Dirac and Weil systems, as shown here. The Dirac equation. So I've got a copy of the Dirac equation. This is from Westminster Abbey, and so. Yeah, okay, thanks. Okay, the Dirac. Is it really that bad? So the Dirac equation includes a mass. The Dirac equation shown up here. Can you hear me? Okay, I think we're okay. But look, without a mass, what we get is massless fermions. And as shown up here, we get a Dirac cone. So for Dirac systems, there's a fourfold degeneracy, so that's built into the Dirac equation. So Dirac cone here would be for massless Dirac fermions. If there's a mass, that just means things are open up. So normally you think of Dirac fermions as being electrons and holes, or particles, antiparticles. In solid state, these are electrons and holes, but they're holes in condensed matter systems. So, and there's a splitting into Weil systems, which so for a Weil system, there is a splitting, and we get a chiral cone that's twofold degenerate instead of fourfold degenerate. So those are the systems that we're looking at. In the case today, mostly Dirac fermions. You have another idea? So for example, cadmium arsenide, one of the first Dirac semimetals, there is a crossing. When you have a crossing in condensed matter, when you have a crossing in quantum mechanics, normally there's an avoided crossing. But in some solid state systems, there's a symmetry. So in this case, there's a symmetry along a plane. So normally this would be a circle of degeneracies, or in this case, I think a sphere of degeneracies, but there are points at which the avoided crossing is symmetry protected, and that's a protected Dirac cone in condensed matter. So that would be a massless Dirac fermion, and if the Fermi level was right here between the filled and empty states, then we would have a topological semimetal with, in this case, two different Dirac cones at the Fermi level. And so that's what we're talking about, is systems like this. Normally in Dirac systems, this would be equals kc, speed of light. This is the Fermi velocity. So k times the Fermi velocity is just the velocity that we get for the quasi-particles in our system, which is pretty big for condensed matter systems in these systems typically. So, but VF is the velocity that I'll use to refer to the thing. But this is the thing that corresponds to the speed of light for normal Dirac systems. Okay, so original Dirac fermions would be graphene. Graphene is a two-dimensional system where it's an array of carbon atoms, but the band structure, and of course this is the set of electrical excitations, has points of contact, and so this makes a Dirac semimetal, but in two dimensions. So this is what I would call a Dirac semimetal. A semimetal is a system that has no gap, but a metal has a very strong overlap at the Fermi level. A semimetal could be something that has a kind of a tentative overlap between two different bands. In this case, there is a touching with exactly no density of states at the touching point for the Dirac point. And actually, it's the symmetry protected also for the case of graphene. So here the Fermi surface, and sorry, I don't have a laser pointer, but the Fermi surface, and there's right at the Fermi surface, by just electron counting, is where the Dirac cone falls. These have very high mobility because of the large Fermi velocity. The mobility is the ability of the system to conduct electricity. So for very practical things, interconnects and electronics, for making high efficiency transistors, these can be potentially very useful systems. The magnetic properties also lead to quantum effects in relatively low fields. What we've shown here is the set of lambda level energies for a Dirac cone system like graphene. In normal electron systems where the energetics is quadratic, the lambda levels are equally spaced. Here we got non-equally spaced lambda levels, but also the splitting can be large in relatively small fields. So that allows us to go into the quantum limit, and quantum limit is usually the notation for a system where essentially all the carriers are in the lowest lambda level. The splitting between lambda levels is the important splitting in the system. It becomes a conductor. The kinetic energy becomes quenched because in 2 dimensions there is a localization of states. And so this is 2 dimensions becomes a 0-dimensional system. And so that's a dimensionality reduction, as long as the temperature is such that the energy splitting is large. So that's our background for graphene. Topological semimetals then are 3-dimensional graphene. So in the case of a 3-dimensional system, we can still have such contact. I showed cadmium arsenide, but it's got arsenic in it. It's really hard to make, and it's a nasty material just because it's very brittle and doesn't work very well. There are other materials, like for example, the zirconium telluride that I'll show, that are very robust materials, and and have interesting Dirac cones at the Fermi level. Now, topologically, the reason these are topological semimetals is they have topologically distinct properties. And that would be related to the crossing point. If you have a crossing point, actually in Berry's original paper, so Berry phase is a topological phase related to the behavior of these systems. There is a non-zero Berry phase going around a crossing point of this type, a non-avoided crossing, if you will. It's that Berry phase that ultimately makes up the topological behavior, because it's distinct from the outside world. So if there's a topological distinction with the outside world, there's a boundary condition, and the boundary condition tells you that there's something interesting could go on at the boundary. Originally, the topological insulator was discovered. That's an insulator whose electron bands are topologically distinct from the outside world. One way of thinking of that is a Dirac system whose mass is negative and goes positive. Of course, in the middle, there's 0 there, and there's a 0 mode at the surface. That 0 mode is the conducting surface states in topological insulators. In the massless case, and so this would be the topological semimetal case, there's still boundary conditions that are interesting. And so in Weil semimetals, the Weil arc, Fermi arc, has been has generated lots of interest. A Weil arc is half of a Fermi surface, and that would be just for a conducting state. So if you go to the surface of a Weil semimetal, it has a strange looking Fermi surface that doesn't continue all around. You can look at this in various ways. This is for a particular model of Weil semimetal, but if you see up on top of Weil electrons, where the degeneracy between spins are broken, has a chirality where the spin and momentum behavior are coupled. And that chirality also carries onto the surface. So in energetics, there's a chirality as well. It's kind of illustrated nicely from this paper. So you can see there's a chirality of the energy, and it winds in a particular direction. But if you have a pair of Weil nodes, which topologically one actually always must have, then if they wind in two different directions, then that winding gives you a peak, and you see that there could be an arc. The arc is just a step in the electron energetics going that goes between. So that's the Fermi arc. Dirac semimetals have more complicated Fermi arcs too, and so these are the topological boundary conditions that make up the behavior of topological semimetals, Weil and Dirac systems. So that's the behavior. And there are a lot of materials that there are a lot of different kinds of topological semimetals that have been identified. Besides just having points, you can have a nodal line semimetal. So this is something that has no analog in particles, but inside a condensed matter system, you can have a line or a curve upon which there's a contact point. And that can also have interesting topological properties. And actually, I'll talk towards the end of the talk about some that we're looking at in our lab. So there are materials that have nodal line behavior. One of the features of a nodal line semimetal is the potential for what's called a drumhead surface mode. So you get a huge density of zero modes of the surface. High density of states is interesting in condensed matter because it can lead to things like superconductivity, which in topological systems could be topological superconductivity, which is nowadays of interest because that might host a Majorana fermion and be, so for quantum computing, there's loads of interest in such systems. But that's one type of feature. Type 2 Dirac systems, actually the nickel telluride is one we're starting to look at in my lab right now. Again, there's no particle analog. The Lorentz invariance is broken in that case. There's also a large density of coexisting states, so interesting distinctive properties in some of these systems. Okay, so specifically for zirconium telluride is a material that has a Dirac cone, and it's not crossed by other states at the Fermi level. So for the nickel telluride system, I showed the band structure there. So again, the band structure is the set of electron states. If you go other directions in K space, there are actually lots of bands crossing the Fermi level. So it's not just a Dirac cone. There's many different states, which are kind of hidden in that particular picture. But for the case of zirconium telluride, there's ZrTe5 specifically. There is one state, and it's right here. It looks like there are multiple ones, but these are multiple pictures of the same thing. And the band structure. So there's a single Dirac cone. It's a massive Dirac cone, meaning, again, there's a gap. There's a gap that opens in this case. But this was identified 5-6 years ago as having interesting properties. Originally, actually, this was studied back in the 80s for being a charge density wave or other interesting conformations. But this was proposed that this could be a basis for a two-dimensional topological insulator. So a quantum spin Hall insulator would be, that's if you can do the graphene thing and peel off a layer of the material, which you can't in this material. That doesn't work very well, as it turns out. But as a bulk system, there's a number of interesting properties, as it turns out. One that got a lot of attention was the chiral anomaly or chiral magnetic effect observed in this system. There was so the chiral anomaly is something in particle generation that gives you an imbalance between particle types. Rick and several groups at Rick actually had a result just about the same time showing in heavy particle collisions generation of something similar. In the case of zirconium telluride or a Dirac semimetal, it's actually a transfer of carriers between different chiral modes in two Weil cones. So that's this behavior. It leads to distinctive magnetoconductive properties. So that's the chiral magnetic effect, but there is, however, a lot of disagreement about what specifically the dispersion is like, whether it really is a point or how this behaves. I will move forward to show this. And actually, there have been several results showing quantum Hall effect behavior shown in this material as well. Quantum Hall effect is an effect normally seen in layered materials, single layer materials, where if you have a two-dimensional electron gas, the discrete separation between energy levels coupled with a localization type phenomenon gives you a very precise measure of conductivity, for example, and a number of interesting effects. In this case, not only the quantum Hall effect, but indications of fractional quantum Hall effect. But this is actually in a three-dimensional system, and this is a system that's believed to have a three-dimensional Dirac cone. This result got a lot of attention. The suggestion was that there's charge density wave formation, which is sort of a layering transformation where three-dimensional sort of spontaneously converts to two-dimensional. So that's the background. There may be other explanations for what's going on here. I'll address that later in the talk. So, with that introduction, I want to discuss the magnetic resonance NMR measurements that we're doing and some of the results we have in we've had in our lab. So nuclear magnetic resonance is basically using the Zeeman resonance of the nuclei as a probe of what's going on inside a material. The nuclear Zeeman levels are RF in frequency. It's a very low energy, so they couple very weakly to the surrounding world. It's the hyperfine interaction between the nuclei that we're detecting, both as far as looking at the spectrum, which gives us a picture of the local fields, so a mapping of the local fields inside the material, but also the relaxation time, and T1 specifically is what is a term we use for the recovery time. It's the exponential recovery to equilibrium. Which is something that turns out to be a very useful fingerprint for what's going on inside the material. It's fluctuations of electron hyperfinite fields and other fields that give locally this behavior. The picture you might have is an electron comes in, and if it's a spin interaction, the spin scattering off the nucleus then can cause the nucleus to relax, because otherwise the coherence of a nuclear spin system lasts a long time. So the T1 and the spectrum, which maps the local fields, are what we're looking at. And so here's an example then of, in ZrTe5, a spectrum. You see here the three peaks. Crystallographically, there are three tellurium peaks, and there are three tellurium sites within the crystal. So zirconium, Te, and the three named peaks up there, the Z and D. NMR is not a highly sensitive technique because of the smallness of the RF quanta, and so this took a line sample of many different individual crystals to do this. But that was what was done by my student Yifan Chen, and these are vapor transport grown crystals that we do in our lab. And this shows then the shifts versus temperature. So what happens is that as we lower the temperature, the actual spectra are shown on the left, and this is a map of the shift positions in ppm but just the small shifts of the resonance position versus temperature. And you see there's indeed a crossover there at a little bit below 100 Kelvin. That crossover in the shift position is a transformation, it's a phase transition in the electrons as the chemical potential moves through the electron states. And so that's, I'll show a topological transformation for the carriers. It actually was proposed that there's a band inversion going on here. So if you think of a Dirac system, normally it's generated by having an inversion. So if you start with an insulator with all the states either filled or empty, and you come close together and make a semimetal, you can actually have an inversion, and that leads to the avoided crossing or the unavoided crossing that gives you a Dirac system. So there's a crossing of states required for this. And that crossing is what can happen if you change, for example, the crystallographic, the crystal size. And in this particular example, the crossing was from a weak to strong topological insulator. I will describe that later on. But so we have an inversion. And this can be seen in the T1. So here's the T1. Remember, the T1 is the recovery time. And in this case, what we observe is also a minimum that occurs at the same temperature as the crossing in the shifts that we saw before. So this is 1 over T1 is the rate. T1 is the time. So this is the rate, actually multiplied by temperature. But this is the behavior. So in NMR, then we have hyperfine interactions. And so our trouble as experimenters is figuring out what's causing those interactions. So what's the source of this thing, and what's the behavior? Well, it turns out this is actually huge as far as the T1 goes. And it's much bigger than we would expect for normal metallic electron interactions. Shown as the red curve there, for example. It actually was shown in, this is Patrick Lee and the Gauka in the early 90s, that there is a singularity or a singular behavior for interaction with orbital interactions with electrons for the case of the carriers are very high mobility. And this is what we have. So the Dirac system has high mobility carriers, and that allows us, it turns out, to, that's the source of the large relaxation rate. Okay, and the broad minimum corresponds then to a topological phase transition as analysis. So there's a lot of equations here which I won't describe, but essentially what's going on here is that the interaction is the sort of interaction I described. So an electron comes in, it scatters off the nucleus. But in this case, the fluctuation is orbital fluctuation. So an electron that comes around, but it can be a long distance away, and it switches into another orbital. In order for that to happen, we have to be at the Fermi level because there have to be filled and empty states available, just because the phase space argument there. And so this is a precise measurement of what's happening at the Fermi level. And it was shown recently that this gives in the three-dimensional Dirac system a quadratic type behavior, which is just the kind of behavior we see here. The minimum occurs when the Fermi level, actually the chemical potential in this case, crosses the Dirac cone, or crosses the Dirac node rather, and that's the general behavior. Okay. Delta is the gap, it's mv squared, so that corresponds to the mass. So the energy gap is the mass. We extended this to include the gap. And so here's a fit. The fitting shows for one particular site, but the fitting for several sites gives us a measurement of the gap. And this is actually gap versus temperature. So we get a precise measurement of the formation of the Dirac gap in this system. You can see that actually it closes and opens. That's what's called a Liftshitz transformation. It's one type of Liftshitz transformation is a fancy word for a change in the topology of the Fermi surface. So the electron band at the Fermi surface is the is the boundary of the filled states. And if that topology changes, that's a Liftshitz transformation, which in this case is a temperature-dependent Liftshitz transformation, which in this case shows the change in topology that corresponds to the topological behavior of the electron bands in this case. Yeah, so here's a picture that is induced by the change of the chemical potential. And it's interesting that the closing of the gap and reopening occurs just at the point where the chemical potential crosses the node, indicating some interesting correlation effects going on in this system. So that's the that's one result. There are three sites. The Z is zigzag because one site's a zigzag, and there's a dimer and there's an apical site. So there are three sites. There's just A, D, Z. So that's the one you mean, like T, E, A, and D. Yeah. So actually, and there are three sites. This just shows two of them that were fitted in this case, but yeah. Yeah, so the maximum, there's a resistance maximum, is that the, or the? Yeah. Yeah, it is, right. So it occurs when the gap is zero. We don't have a full explanation for that. It's unclear what causes that. There's a lot of electron interactions here. So the apparent explanation is that the gap opening is in part induced by interaction. So when you cross the node, that's the minimum density of states. Actually, in principle, no density of states at that point. So you have a minimum electron density. And so if the electron density helps drive the gap opening, then that would explain. So that's what we believe is going on here. Now, that's the statement about correlation effects going on. So that's, yeah, the interesting behavior here that occurs. And NMR is particularly sensitive to what's going on at the Fermi level. So, for example, photo emission is very nice for mapping out the overall momentum dependence of the bands, but we have a particular sensitivity to what's going on locally, so we can see very precisely what's happening just at the Fermi level, which of course is what's most important for electron systems of this type. So, sorry, I hope my voice holds up. But anyway, we did some electronic structure calculations, and this also confirmed the topology change. This shows a general picture. Actually, our result is that the reversal, it was believed that there's a reversal of the symmetry. Weak versus strong topological insider has to do with the different invariants and which surfaces have gaps. And in any case, our proposals now agrees with general behavior, but there is a transformation, a Liftshitz transformation. The gap closes and opens, and in the process, there's a change in the topology of the bands, and that's the general result. So, and by the way, so Peter asked me to comment on the Parisi and the recent Nobel Prize addressed complex behavior, and this is sort of complex behavior. There's not too much connection between these results, but spin glass systems have a certain topological behavior, or at least they can. And so there are certain properties. If you go to a quantum spin glass, you can have a quantum spin liquid. Those definitely have topological properties in the sense that they're long-range behaviors, and you can't see locally the behavior of those systems and understand the topology. It's a long-range thing. Topological phase, topological defects, topological states, that join different phases. The Higgs separates as the topological defects too. Those are all topological in physical space. Our system is topological locally, and it's different. And the topology is momentum space. So there's a complex sort of topology going on here, but it's distinct from sort of topological defects and topological systems of that type. Now, we should probably have a theorist maybe address whether there's some other connection between the spin glass systems and this. But as far as I know, this is somewhat far removed from the physics of the Nobel Prize. So but that's the picture. So this is topological. I mentioned the Berry phase, and there's behavior of the electron bands. But if you take various integrations through momentum space, it's the behavior of those bands in momentum space that makes them topologically distinct from other systems or the outside world and things like that. So that's the topological behavior of these systems. No. Okay, so ZrTe2 is so we figured, okay, zirconium Te5, zirconium ditelluride is another system, and it's a system that has indications of topological superconductivity. We thought we would look at this system also, and actually it turns out that something similar to the relaxation behavior of the observed in the ZrTe5 is observed here also, and so this gives as also an effective local probe of what's going on with the electron. What I'm going to do, however, we got started late, and I'm going to jump to the conclusion of this one, which is here. And actually, this system only looks like a three-dimensional topological semimetal at high temperatures, I mean, at low temperatures, and there's actually a point at which it starts to look like what I call 3D graphene, which is basically just a set of essentially uncoupled layers. So we can see that also from the T1, the relaxation behavior gives us this picture because of the behavior that we expect of such systems. But I'd like to actually move on to another system. Zirconium silicon telluride is the nodal line semimetal that I mentioned, and probably just as much as ZrTe5 in condensed matter. This family. So I have zirconium silicon selenide, but there's a family of these three component materials that has attracted a great deal of interest because of the nodal line, again, unencumbered by other states. It's a rather complicated nodal lines, a network of nodal lines in this case, but there are a number of interesting properties of this system. One is that in high fields, there is apparent excitonic behavior because of the having a nodal line instead of just a nodal point. You have a high density of Dirac states, and that high density of Dirac states mean you can have strong interactions between carriers, and so there's strong electron-electron effects in these systems. Is one of the interesting behaviors, and also the zirconium silicon telluride is believed to have a very large, a relatively large drumhead mode, which is the surface state that I defined earlier. So maybe interesting for surface superconductivity, or as a catalysis system, because you also need large density of states on the surface. So there's a No. So the nodal line, that's a bulk. So the bulk property of the band, in that in the bulk you have a crossing. That would be a Dirac point. So in this case, I have a Dirac circuit. That's usually called a nodal line. In this case, it's actually a circuit, and there's a chain or an interesting set of circuits. But yeah, so the surface states are kind of a projection of those bulk states on the surface, and solids can have distinct surface states, and those are the surface states, but they have a direct connection. There's this thing called bulk boundary correspondence, which is a topological behavior, and it has to do with the Berry behavior. So there's a correspondence between them, but they're different things. The surface states are never termed nodal lines in that sense. So it's not a node. It's really a Fermi edge. It's a bit of Fermi surface. So so no, I wouldn't call it that. It's something a little different. Okay, so NMR on this system. In this case, we collaborate with a group from Penn State, and we have a single crystal of this material. This shows the behavior for two different orientations. And what we see is here, there's an interesting minimum. And so this is also a crossing of the type we saw for the zirconium TE5. That crossing has the log singular behavior, which I skipped over for the ZrTe2, but has a log singular type minimum that corresponds to a quasi two-dimensional Dirac system. And the quasi two-dimensional corresponds to the fact that it's a nodal line and not just a point. So that's the behavior. We actually show that the node is very close to the Fermi level and has very little dispersion, meaning the energy is essentially constant along the node. So that was the result there. Now calculations show that there is one of the nodes that's protected against spin orbit coupling. And that's the one that's a map of momentum space. So along the R to X line, which happens to be right at the Fermi level for this system, there is a line of nodes, and that's the thing you see in the band structure there. There is a rather complicated Fermi surface, but this Fermi surface is made up of nodal lines that are going around and about through the through momentum space. But it's right here along this line because it's at the edge. There's a protection, and it's a symmetry protection, as I mentioned, a crystal symmetry, the non-symmorphic symmetry of the particular crystal structure of this material that protects that nodal line from having a gap. And so it's a protected nodal line, meaning there's guaranteed to be a zero mass nodal line. And the zero mass is the reason for the sharp point there. The sharp point is generated as the chemical potential moves across the nodal line in energy. And the reason that happens, we don't know. Actually, the motion of the T dependence. Sorry, that wasn't my next slide. Anyway, the T dependence, we don't completely understand the mechanism for it, but we do understand the NMR results, and we can model the shifts. The modeling of the shifts actually has to do with the modeling of the Landau splitting. And if it's a two-dimensional system, that is just like a stack of graphene layers. And that stack of graphene then layers has Landau levels that are well defined. So these are discrete Landau levels with splittings that we can understand. And it's the change in the free energy of the electrons, those Landau levels, that leads to the diamagnetism. And graphene also has a very large diamagnetism, and is due to this effect of the diamagnetism of the carriers. So, and this is a model, and the model only works for the little green line there. It doesn't work at other temperatures, but it gives a reasonable fitting to the shift behavior. The T1, so again, the relaxation rate, 1 over T1, also has a minimum, and it also has a minimum at the same temperature. It's a log scale there, but you see the T minimum there is treated. And we did a fitting according to that complicated model with all the equations on it, which my earlier slide, which, but the fitting was done in conjunction with the fitting for the shifts. And together, they have the same behavior. And so that's the minimum shown in the curve over there. So actually over a limited temperature range, this does a very nice job in fitting the behavior. So fitted together, we have Dirac electrons. This is equation from the behavior. This is for the two-dimensional case where there's a factor of 3 halves between the two. And that actually works for both orientations. So you can see the black and the blue are the two orientations for this case. So it is along and perpendicular to the nodal line, which in this case, the nodal line is a one-dimensional thing. Well, the departures at high temperatures, we realize there's something else interesting going on. And so what we did was we kind of drilled down into the band structure. We realized there's an interesting conjunction of different energy states going on here. And this corresponds to what is a singularity in the density of states due to a conjunction of nodal lines. Actually, there are 3 nodal lines very close together. And those 3 nodal lines happen between what's called a Van Hope singularity. Van Hope singularity just means a switching or a singularity in the density of states that comes from a change in the energetics as you have a crossover. In this case, there's a crossover from the node at the middle and the 2 nodes at the outside. The protection against gapping is only along that line. But when you turn on spin orbit coupling, okay, so what you have to imagine is 2 cones here that are overlapping. There are 2 cones overlapping. There is not a Dirac cone at the juncture between them because it's got a quadratic dispersion. But there is a boundary between them. When you turn on spin orbit coupling, you notice that the lens-like thing has turned into a separated circle. So that would be a complete splitting of states and generation of a gap. It could become a semiconductor if there weren't all those other nodal states going on there. However, there's a protection against gap formation along that line. And so when you do that, that actually causes a singularity. In 2 dimensions, that singularity is a log singularity. So this is a 3-dimensional material, but it behaves like it's a 2-dimensional material in the sense that there's a large modification of the density of states. Here's the picture, and this was published this year. You can't see very well the reference, but this shows the Fermi surfaces versus energy as you go near the Dirac system. Doing density functional calculations, there's some averaging going on, but we can actually see the peak there. That's actually a log singular peak since this is a 0 dispersion nodal line. So this gives the behavior that there is this interesting additional feature. Twisted bilayer graphene has attracted lots of interest lately. So I showed graphene as 1 layer. Imagine you have 2 layers put together. If you put a whole bunch of those layers together, you get graphite. And graphite is kind of like ZrTe too, like I said. So 3-dimensional graphene is a graphite because the coupling between those layers is very little. And so graphite is almost like having conduction only in the layers. There's just a very tiny amount of dispersion in graphite that comes from the coupling between the layers from the 3-dimensional material. So in this case, though, in the case that you take 2 layers and the twisted bilayer graphene is twisted by a well-measured angle of 1.3 degrees, but it turns out that that gives you also a Van Hope singularity because you have 2 Dirac singularities very close to each other in momentum space. That's one of the features that drives the properties of twisted bilayer graphene. Then in addition, because of the interesting sort of moire structure, the periodicity of that system leads to also very flat bands, as it turns out, interesting properties. So this is in some ways an analog. However, in this case, there are actually 3 Dirac cones, so 2 very close together, and so this is maybe an interesting platform for exotic new states. So that's a result that comes from that study. Okay, so I've got a few minutes left, I hope, and I will talk about the last topic, which is actually circling back to ZrTe5. This talk was put together in kind of a chronological order here, but more recently, we studied the ZrTe5 in a different orientation. So the initial studies were done with a magnetic field along the needle direction where the perpendicular Fermi velocity is not so big, And so there, if you look at, for example, magnetotransport or other properties, there's not so much difference in the electronic properties if you put the system in a magnetic field versus not putting it in a magnetic field. However, if you put the system in a perpendicular magnetic field, these look like ribbons, so that if you put the field perpendicular to the ribbons, it's not a two-dimensional material, but the Fermi velocity is the highest perpendicular to that field direction. So in that plane, there's the largest field response, and that was the orientation in which the quantum Hall effect behavior was observed. That's actually a field-induced quantum Hall behavior. This is the phase diagram from that work. And if you notice, the fields are actually very small. So this is temperature, the magnetic field. We're at in a magnetic field of 9 Tesla. However, actually our system has more electrons, so we're in the regime of the quantum Hall effect in our crystals also. When you go to high temperatures, you go over the peak, and the electron to hold tight just means we go over the peak, and so the conduction type changes character. And as we showed, there's actually a Liftshitz transition between those. But at lower energy, at lower temperatures, what can be seen in a magnetic field is there a sequence of transformations. So quantum Hall effect is the layered type conducting behavior that I mentioned. Fractional quantum Hall effect is another type of magnetotransport behavior, but at higher fields, at very low temperatures, layered systems in some cases also have unusual properties where the electrons pair up or they join up in correlated states, and that's the fractional quantum Hall effect. There are indications of both of those in the system. There are other interesting indications here. One is that the dispersion is now realized maybe a little bit different than what was originally believed. So even though the gap is closing and opening, and we showed that Dirac cone is a three-dimensional Dirac cone because of the T1 behavior very close to the node, it actually has a small dispersion. It's not just a point. So, okay, so our results are these. So in this orientation, we actually see a number of interesting new transformations. One is that instead of just the minimum in the 1/T1, this system is going down and it has a quadratic behavior, very much like the behavior in the other orientation. However, this is interrupted by a sudden drop, and there's a log scale over there. We see that the 1/T1 has dropped by more than an order of magnitude. That actually is the density of conducting states that has dropped by more than an order of magnitude. So this is actually a transformation between two different states. And the sudden transformation corresponds to a lowering of the conductance. And in this particular case, the NMR is sensitive specifically to the Dirac electrons. So it's the Dirac electrons that have disappeared. There also is a little jump in the shift, and the shift becomes constant. The explanation for that, 1 minute. Okay, so we did a modeling for this. Actually, it turns out even though the Dirac cone is isolated, there is another band close by. And if you simply require the number of electrons to be constant, we found that in general, the chemical potential will automatically cross the Dirac cone at about the temperature where this phase transformation occurs. And so it's just electron conservation that causes this to happen. So we can model this actually very well, and that explains the change in the chemical potential. So the gap state then corresponds to a change in system, but it can't be the charge density wave state that was proposed for the quantum Hall effect state, because charge density wave state requires there to be a lot of carriers. In this case, the chemical potential is going across the nodes. There aren't any carriers. So the best explanation turns out to be an exciton insulator. An exciton is a kind of pairing up of electrons in holes. This is something that in condensed matter actually has been looked for a long time. it was realized in the 60s that this is a BCS-like pairing. So the condensate is very much like a superconducting condensate. But in this case, it turns into an insulator. And it turns into an insulator as the electrons and holes pair up and they go into a bound state. That's the result here. We could also see that the low temperature system is a spin polarized system. So that corresponds to the quantum Hall state. The details of why this system becomes a quantum Hall state, we're still not sure, but we get some additional information about this state also. And so that's the general result. And so yeah, I'm out of time. So here's my summary. I will jump actually to this page and show you find now at Cornell and Nodal, Gosemi did a lot of the computational work is now at LSU, and Ray Lee is here also with the 3 of my students, and this is our team. So thank you.
I would like to know, with all this wonderful, new, very complex stuff, if there's anything that will probably be distilled down so that in 5 years or so, we will be able to say to our seniors, well, 30 years ago, we did 30 phase. Now we have.
Among these results,
Right.
so,
What would be the single?
oh, I don't know. I'm not a very good future predictor, but I'm not sure. In this case, you know, these are very nice examples of the interesting topological properties, but there's been a successive of new things. So I think there will be a number of additional interesting results related to this new physics that's been opened up. But where it will go, I'm not sure that I want to hazard a guess exactly, because I'm sure I'll be wrong. But in any case, say again? Yes. Yeah. That's a theoretical novelty that's been of interest for a long time. There's lots of interest. There are several crystal systems that right now are believed maybe to have such systems, but there are phase transitions going on. You know, whenever you have a change in electronic state, maybe you can use it for something. So potentially, maybe this could be used for some sort of a switch, a new memory device, or something like that. So there's, and you know, so these are connected to practical systems that are that could certainly be used in conjunction with other semiconductor devices and things. But mostly, it's a tour de force to see the behavior. Questions? Oh.
Can I ask a question or nobody is listening?
He says yes.
Maybe that means he wants to know. Maybe you can read it from the chat.
Alexi, can you put your question in chat? I'll see if I can unmute.
Okay. Okay.
Or you can unmute rather, sorry. I don't think we can hear them. This has always been a problem in the past. So
Put it in chat though. Read the chat.
yeah.
If you go to chat.
Oh, I'm looking at it. So he says,
Oh.
yes, he has a question. Oh, I thought you could see it up there. I can see it in front of my Zoom. Oh, okay. This is direct Zeeman split in the strong magnetic field. Yeah, ZrTe 5 has a huge G factor. It's about 22 or something like that. So that was actually a model had a Zeeman splitting of the Dirac cone of the lambda levels. So it's an interesting question in low fields how the Dirac cone behaves versus high fields. At high fields, we modeled this as discrete Landau levels, which are spin split, and the spin splitting is large. There's also this question of whether a Dirac cone and magnetic field also can split into two Weil cones, or actually can split in different ways. So definitely there is a splitting. We didn't model it that way because that's sort of the continuum limit for the Dirac cone. Our field is large enough that we're, sort of quantum limits. So we modeled this in terms of discrete Landau levels, and the splitting there is big. I don't know whether the splitting in this case is the type where the single Dirac cone splits up into two Weil cones, or precisely what the behavior is in that case. It depends. It's rather dispersion dependent for the Dirac cone. So there's some questions about that, but that's how we modeled it, was in terms of the Landau splitting.
There are no other questions. I'd like to thank your speaker again.